Welcome to Still Science Lab. Tonight, we explore about physics-tested time itself, and the results are terrifying. We live our entire lives under a quiet, unexamined assumption. We believe that while the universe is a place of endless motion and violent transformation, while stars detonate, galaxies collide, and planets weather away into dust, the fundamental rules governing that chaos remain perfectly, eternally still. We trust that the laws of physics are the unbreakable foundation of reality, a permanent stage upon which the drama of the cosmos plays out. It is a comforting thought. It gives us a sense of solid ground in an otherwise terrifying and infinite void. But what if the stage itself is moving? What if the mathematical bedrock of existence is shifting beneath our feet, so slowly that we simply never had an instrument precise enough to notice? To understand how we finally reached a point where we could even ask this question, we have to look at humanity's long, obsessive relationship with measuring the passage of time. For millennia, our concept of time was dictated by the macrocosm. We looked to the sky. We measured our days by the rotation of the Earth, our months by the phases of the Moon, and our years by the orbit of our planet around the Sun. We built sundials, water clocks, and eventually intricate mechanical pendulums to chop the day into smaller, more manageable pieces. In the 20th century, we abandoned the macrocosm and looked to the microcosm, harnessing the steady vibration of quartz crystals and the energetic transitions of cesium atoms to define a single second. Every step forward in timekeeping technology was a step toward order, an attempt to impose a strict, unyielding grid over the messy, chaotic flow of reality. But recently, in a quiet, windowless laboratory in Boulder, Colorado, a team of scientists pushed this obsession to an absolute physical limit. They built a machine that forces us to confront a terrifying possibility about the very nature of existence. It does not look like any device you would recognize as a clock. There is no face, no sweep of a second hand, no ticking mechanism, and no pendulum swinging rhythmically in the dark. At the very center of this sprawling assembly of complex lasers, tangled cable trays, and heavy vacuum chambers sits a single, solitary atom of aluminium. It has been intentionally stripped of one of its electrons, giving it a slight positive electrical charge, and it is being held perfectly, flawlessly motionless inside a trap forged from invisible electromagnetic fields. The environment inside this trap is one of the most extreme isolated pockets in the known universe. The temperature has been carefully dropped to a whisper above absolute zero. At this extreme thermal limit, the frantic, vibrating heat energy of the quantum world is almost entirely suppressed. The atom does not glow. It does not wander. It exists in a state of profound, absolute stillness. And that stillness is the entire point. A moving atom is a blurred atom, and a blurred atom cannot keep perfect time. Suspended in this frozen, artificial void, the single aluminium ion oscillates between two specific energy states at a frequency of such staggering regularity that the machine built around it has become the most accurate clock ever created by human hands. To call this apparatus a clock almost feels like a failure of language. It measures the passage of time down to the 19th decimal place. To understand the sheer, incomprehensible scale of that precision, you have to compare it to the previous world record, which reached the 18th decimal place. Even that older clock was so profoundly accurate that if you had started it running at the exact moment of the Big Bang, 14 billion years ago, it would not have gained or lost a single second by today. This new instrument in Colorado is roughly 41% more accurate than that. It is a machine that measures duration with a fidelity that seems almost alien. We are now measuring time with an accuracy that has no ordinary comparison because there is absolutely nothing in ordinary life that requires it. This raises an immediate, practical question. Why build it? No GPS satellite navigation system requires this level of precision. No deep space probe tracking, no financial trading algorithm, and absolutely nothing that anyone does with the concept of time on a daily basis comes anywhere near demanding a clock tuned to the 19th decimal place. We have crossed a boundary where engineering leaves the realm of utility and enters the realm of fundamental cosmic interrogation. When you push an instrument to this absolute extreme, it stops being a device for merely telling time. It quietly transforms into a probe. It becomes a highly sensitive, conceptual scalpel, capable of slicing open the fabric of reality to reveal the hidden mechanics underneath. Below a certain threshold of accuracy, a clock just tells you what time it is. Above that threshold, a clock starts telling you things about the physical universe that nobody specifically asked it about. It becomes a detector for anything that could change the rate at which time passes, or change the physical constants governing the very atom doing the ticking. The aluminum ion clock in Boulder crossed that threshold in the summer of 2025, and the very first thing it turned out to be precise enough to check was a question that strikes at the heart of our cosmic architecture. It began listening to the fundamental constants of nature to see if they were actually holding still. This requires us to carefully unpack what a fundamental constant actually is, because it is an idea that is easily misunderstood, and getting it right is worth your time. When physicists write down the equations that describe the universe, from quantum mechanics to general relativity, certain numbers appear over and over again. They are the fixed mathematical pillars that hold all of our theories together. The gravitational constant, which determines how strongly mass bends space-time and how tightly the Earth holds you to its surface, is one of them. Then there is the fine structure constant, a deeply mysterious and highly specific number that dictates exactly how strongly electrons interact with light. This specific number is what determines how atoms bind to one another, how chemistry functions, and ultimately, how the physical material in your own body behaves and holds its shape. These numbers are the foundation of everything. They show up everywhere. They are the fixed points that everything else is calculated against. But here is the quiet, deeply unsettling truth about them that is rarely emphasized in textbooks. Nobody knows where they come from. None of these constants are derived from a deeper mathematical theory. No brilliant physicist has ever produced a theory from first principles proving that the fine structure constant absolutely must be the exact value that it is and could not have been anything else. We only know these numbers exist, and we only know their values because we went out into the universe and measured them. We write them into our equations by hand because the experimental data demands it. And this is where the existential dread begins to creep in. A mathematically derived necessity cannot change. A pure concept of logic is eternally true. But a measured quantity has no inherent obligation whatsoever to remain static. If these foundational numbers are not anchored to some deeper, unchangeable theoretical truth, then there is absolutely no fundamental physical reason they cannot drift. They could be slowly, imperceptibly sliding, shifting in a way that nobody would ever notice with an ordinary instrument. For decades, we have operated on the assumption that they are eternal. We assumed that the gravitational constant that governed the collapse of the very first primordial stars is the exact same gravitational constant governing the orbit of the Moon tonight. We assumed that the fine structure constant that allowed the first carbon atoms to form is identical to the one binding the DNA in your cells right now. But what if they are moving? What if the universe is not a static machine, but a shifting, evolving environment where the rules themselves are subject to change. To catch a drift that subtle, a drift happening on a cosmic timescale, you would need an instrument of unimaginable sensitivity. You would need a machine where a change in the 14th, 15th, or 16th decimal place of a fundamental constant would register as a visible, physical discrepancy. That is exactly what the trap in Colorado was designed to be. It was built not to assume, but to check. I want you to sit in that laboratory in Boulder for a moment and truly digest the weight of what is happening there. Imagine you are standing in that room. It is not a cinematic environment. It is a grey, highly technical space like any other, filled with equipment racks, thick cable trays running along the ceiling, and the relentless, low, steady hum of cooling systems that never switch off. There are no windows, because even the slight thermal variation of sunlight would be a nuisance. Resting on a standard metal workbench in front of you is a vacuum chamber roughly the size of a large cooking pot, wrapped in a maze of wiring. And somewhere deep inside that silent darkness, suspended in absolute nothingness, held by fields you cannot see, is one single atom. It is not doing anything spectacular to the naked eye. It is simply oscillating back and forth between two energy states at a rate so regular that if you set it running at the birth of the universe and came back now, it would still be right. Nothing about the room feels historically significant. There is no dramatic countdown. Nobody is watching a screen with their hands over their mouth in shock. There is just the hum of the equipment, and a machine performing the most precise act any object built by human hands has ever performed. And what that machine is quietly reporting back to the small number of people who understand what they are looking at is that the numbers underneath everything might not be holding still. The absolute bedrock of reality might be slowly moving. This is not a story about a sudden, violent catastrophe. It is not an alarm going off. It is a story about a series of very careful, very quiet measurements designed to answer a simple question, which have collectively produced an answer nobody knows what to do with. It is the slow, creeping realization that our ultimate blueprint of the universe might be written in fading ink. If the constants of nature are drifting, it forces a question that nobody quite knows how to ask properly. If something is drifting, it must be drifting with respect to something else. It must be changing against some kind of backdrop. If a ship drifts, it drifts across the surface of the ocean. If the parameters that govern the physical universe are sliding, what exactly are they sliding through? The immediate, intuitive answer is that they are changing over time. They are moving through time the way a car moves through a landscape. But if you apply that answer to the fundamental constants of physics, you instantly break the conceptual architecture of modern science. Since the dawn of the 20th century, we have viewed time as a feature of the physical universe, a dimension woven together with space, heavily influenced by gravity and velocity. Time is supposed to be a consequence of the laws of physics, a feature that emerges from the equations. But if the laws of physics themselves have a cosmic history, if the constants that dictate how mass, energy, and space-time interact are changing as the eons pass, then the laws are existing inside of time. Time suddenly stops being a byproduct of the universe and becomes the ultimate, overarching container in which the universe happens. This completely inverts our entire relationship with reality. It means you cannot derive the nature of time from the laws of physics, because the laws of physics are downstream of time itself. Time would be promoted to the most fundamental, irreducible feature of existence, the one true constant that does not come from anything else, the ultimate stage that remains even when the actors and the script are constantly being rewritten. This single, incredibly delicate measurement of an aluminum atom threatens to tear down the fortress of eternal, unchanging physical law that we have spent centuries building. It suggests that the universe we observe today is just a temporary configuration, a passing phase in a cosmic evolution so vast and slow that it completely defies human comprehension. The physics that allow stars to burn, planets to form, and life to breathe might just be a temporary window of stability. We built a clock to measure the universe with absolute perfection. But instead of confirming our mastery over nature, the machine has quietly turned around and whispered that we do not even know what the rules are. We are staring into a microscopic void, watching a single atom tick in the dark, and realizing that the concept of time is vastly more terrifying, deeply mysterious, and far more fundamental than we ever dared to imagine. As we stand on the precipice of this new, unstable reality, we are forced to ask a question that strips away everything we thought we knew. If time is the ultimate force that commands even the laws of physics to change, then what exactly is time? There is a profound, almost primal comfort in the rhythmic ticking of a clock. When you sit in a silent room and listen to the steady, mechanical beat of a second hand sweeping across a dial, you feel anchored. We intuitively believe that this rhythm is a universal pulse. We build our entire civilization, our schedules, our historical records, and our emotional lives upon a deep, unspoken assumption about the architecture of reality. We assume that the universe possesses a master clock. We assume that the single second passing you by in this exact moment is the exact same second passing by your friends across the city, the astronauts orbiting the planet, and the distant, burning stars drifting in the deepest oceans of deep space. For centuries, this intuitive feeling was not just human psychology. It was the absolute bedrock of scientific dogma. In 1687, Isaac Newton formalized this comforting illusion, declaring that absolute, true, and mathematical time flows equally of its own nature, without relation to anything external. He pictured time as a vast, invisible river, an eternal background structure, carrying all of creation forward at exactly the same speed. It is a beautiful, deeply uniting concept. It implies that no matter how vast the cosmos is, we are all sharing the exact same present moment. But the universe is completely indifferent to human intuition, and it is under no obligation to validate our comfort. The Newtonian river of time is a mathematical mirage, an artifact of our incredibly slow physical speeds and the relatively weak gravitational environment of our small rocky planet. When Albert Einstein dismantled this classical picture of reality in 1905, he did not just adjust a few mathematical formulas, he completely shattered the concept of a shared universe. He revealed that time is not an external, independent stage upon which the events of reality play out. Time is a physical dimension, intimately woven into the three-dimensional fabric of space, creating a unified geometry known as space-time. And this fabric is entirely malleable. It stretches, it bends, and it warps. Physics has unequivocally proven that time is not a universal metronome. Instead, it flows at wildly different rates depending on two fundamental forces, gravity and velocity. This is not a theoretical abstraction confined to the chalkboards of theoretical astrophysics, nor is it an exotic phenomenon that only occurs at the crushing event horizons of distant black holes. It is a physical reality that you are actively participating in right now. The first undeniable, earthly proof of this localized time occurred in a setting so incredibly ordinary that it almost defies the profound, reality-breaking nature of the discovery. In 1959, two physicists named Robert Pound and Glenn Rebka designed an experiment to test whether time genuinely runs at different rates within Earth's own gravity well. They did not require a massive particle accelerator or a deep space probe. They simply went to a brick building on the Harvard University campus and utilized an internal stairwell that was 22.5 meters tall. From the bottom of this tower, they shone a beam of gamma rays upward to the top. Gamma rays are simply high-frequency light, and the oscillating frequency of light acts as an incredibly precise ticking clock. As the light climbed upward, fighting against the downward pull of Earth's gravity, it lost a tiny fraction of its energy. When they measured the light arriving at the top of the stairwell, they found a microscopic, almost incomprehensible shift in its frequency. The shift was just a few parts in 10 to the 15th power, which is a decimal point, followed by 14 zeros and then a 1. But that impossibly small number matched exactly what Einstein's theory of general relativity had predicted 52 years earlier. The experiment proved, definitively, that time runs slower at the bottom of a tower than it does at the top. I want you to pause and feel the heavy, existential weight of what that actually means. In a completely ordinary building in Massachusetts, while hundreds of students casually walked up and down the staircases completely oblivious to the physics unfolding around them, these two men measured the fracturing of time. The simple, everyday act of changing your altitude, of stepping up a flight of stairs or taking an elevator to a higher floor, literally changes the rate at which you travel through the fourth dimension. A person living on the ground floor of an apartment building is actively aging at a slower rate than a person living in the penthouse suite above them. Their biological clocks are ticking at different speeds. Their realities are subtly, irreversibly drifting apart. We have normalized this bizarre, relativistic behavior of time so thoroughly that we have quietly baked it into the digital infrastructure of our daily lives. Your phone knows exactly where you are right now because it communicates with a constellation of global positioning satellites orbiting roughly 20,000 kilometers above the Earth. Because those satellites are sitting much higher up in Earth's gravitational field, and because they are moving at high orbital velocities, the atomic clocks they carry run faster than identical clocks sitting on the surface of our planet by about 38 microseconds every single day. 38 microseconds is a duration so infinitesimally small that your biological nervous system could never register it. But the mathematics of global navigation are so exquisitely sensitive that if aerospace engineers did not constantly correct for this temporal drift, the positioning errors would accumulate at roughly 11 kilometers per day. Within a matter of hours, the entire navigation network would become entirely useless. Every single time you look at a digital map on a screen, you are relying on a complex machine that only functions because it accounts for the terrifying fact that time is not uniform across space. But the strange isolation of time dilation is not restricted to towering skyscrapers or satellites orbiting in the freezing vacuum of space. The isolation reaches far deeper, creeping into the microscopic boundaries of our own anatomy. In 2021, a team of researchers at Wheeler in Boulder, Colorado, performed an experiment that pushed this existential isolation to a terrifying new extreme. Using highly advanced atomic technology, they measured the difference in the flow of time between two layers of atoms, separated by a vertical distance of just 1 millimeter, 1 single millimeter. That is roughly the thickness of a standard credit card. The precision required to detect this microscopic time difference involved measuring a decimal point followed by 20 zeros before reaching a meaningful digit. And yet, the difference was unequivocally real. The atoms sitting at the top of that microscopic sample experienced time passing at a fractionally faster rate than the atoms sitting at the bottom. This perfectly matched the predictions of general relativity for objects sitting at different heights in a gravitational field. This is perhaps the most intimate and deeply unsettling physical measurement ever recorded. It means that the warping of space-time is not something that just happens out there in the sprawling darkness among swirling galaxies and supermassive black holes. It is happening right here, across the fragile, finite dimensions of your own biological frame. Right now, as you sit or lie perfectly still in a room, the sheer mass of the planet beneath you is pulling on the invisible fabric of reality. The space at your feet, being slightly closer to the center of the Earth, is very slightly more curved by gravity than the space at the top of your head, because the fundamental rate of time depends entirely on that precise gravitational curvature. Time is passing fractionally faster up at the crown of your head than it is down at your feet. You are not a single, unified entity moving smoothly through a universal river of time. Your physical body is aging as a gradient. The top of you is actively aging faster than the bottom of you. Every single time you stand up, every time you lie down to sleep, different parts of your body are keeping slightly different time. There has never been a single moment in your entire life when the top of your head and the soles of your feet agreed on exactly what time it was. You are a biological mosaic of differing temporal realities, stretched across a local warp in the geometry of the universe. You might try to dismiss these microscopic fractions of a second as mere laboratory curiosities, strange numerical quirks of theoretical physics that have no bearing on the grand emotional sweep of the human experience. But time dilation is cumulative. It adds up over distance and duration, and we have already measured its undeniable effects on the lives of actual human beings by name. For decades, physics professors have used the thought experiment of the twin paradox to explain the bizarre consequences of relativity to their students. The classic scenario describes one twin who travels at high speeds into space, returning home only to find they have aged less than the sibling who remained behind. Today, this is no longer a chalkboard thought experiment. It is a documented medical and historical reality. Astronauts who spend 6 months orbiting the Earth aboard the International Space Station routinely return to the surface, having aged measurably less than the rest of the human population. When American astronaut Scott Kelly spent roughly 340 days living in orbit, hurtling through the vacuum at immense speeds, he was actively traveling through a different flow of time. When his capsule finally plummeted back through the atmosphere and he returned home to solid ground, he was measurably younger than his identical twin brother, Mark, who had stayed safely on the Earth. The mathematical difference in their biological ages worked out to roughly 5 milliseconds. 5 milliseconds is an almost imperceptible flutter of reality. It is less than the time it takes for a hummingbird to beat its wings a single time. It did not alter Scott Kelly's physical appearance. It did not change his health, and it did not allow him to cheat death in any meaningful biological way. But the raw, philosophical implication of those 5 milliseconds is absolutely staggering. When Scott and Mark Kelly reunited, standing shoulder to shoulder in the exact same room, breathing the same air, and engaged in the same conversation, they were not sharing the same temporal history. Two human beings who were born into the world at the exact same moment, starting with identical biological clocks, had lived through fundamentally different amounts of duration during the exact same stretch of history. They had experienced different quantities of time. Their nows were simply not the same now. Einstein worked out the full mathematical version of this terrifying isolation in 1905, and it is a reality worth taking deeply seriously rather than filing away as an abstract academic matter. He showed definitively that two events which are completely simultaneous for one observer are physically not simultaneous for an observer moving relative to the first. This is not a biological trick of human perception. It is not an optical illusion produced by signal delays or the imperfect limitations of our measuring instruments. It is a genuine structural feature of the geometric fabric of space-time. Events genuinely occur at the same time in one frame of reference and at entirely different times in another, and neither frame is considered more correct than the other. Both perspectives are equally valid descriptions of physical reality. If two identical twins, separated by just 400 kilometers of altitude and a burst of orbital velocity, can physically diverge in time, then this unforgiving principle holds true for every single object in the cosmos. Every burning star, every cold rogue planet, every drifting comet, and every single human being on this earth is experiencing a completely unique, isolated flow of time. When we look up at the night sky and see the sprawling, glowing tapestry of the Milky Way, we naturally want to assume that all of those distant, swirling worlds are existing simultaneously in one grand, cosmic present. We imagine a vast, universal now sweeping across the galaxy like a wave, synchronizing all of existence. But the laws of physics demand that we violently abandon this illusion. These experiments physically demonstrate that there is no single shared present anywhere in the universe. There is no universal clock ticking in the background of reality. There is no master time that everyone shares. There is no cosmic metronome that the universe keeps step with. The concept of a single present moment, a slice of reality that is happening simultaneously everywhere, is not a feature of the universe at all. It is a psychological projection, a biological coping mechanism we invented because our slow-moving brains could not perceive the relativistic warping of reality. We only possess local time. Your present moment is an entirely local phenomenon. It is real for you, and it is real for everything in your immediate vicinity, but it is dictated exclusively by your specific velocity and your exact depth within a gravitational well. This is the ultimate, inescapable isolation of the physical universe. You are an island in space-time. No matter how closely you hold someone, no matter how perfectly synchronized your digital watches are, you can never truly share the exact same moment with them. We are all drifting through the dark, each of us trapped in our own localized bubble of time, aging at our own unique mathematical rates, moving irrevocably forward into a future that is entirely, terrifyingly our own. The comforting illusion of a shared reality is dead, replaced by a universe infinitely more strange, where the passage of time is a lonely, intimate phenomenon that belongs to you and to nothing else in existence. There is a relentless, driving force that dictates the entire structure of the human experience, an invisible current so deeply woven into our consciousness that we rarely pause to question its existence. It is the unyielding, forward march of time. Every moment of your life is defined by a strict, non-negotiable sequence. You possess clear, vivid memories of the events of yesterday, but the events of tomorrow remain entirely hidden behind an impenetrable veil. When a ceramic cup falls from the edge of a table and shatters on a hard floor, the pieces scatter in a chaotic burst of energy. You have never, in the entire history of human observation, seen those scattered shards spontaneously vibrate, reassemble themselves into a perfect cup, and leap backward through the air to rest quietly on the table. You are born, you age, your cells slowly degrade, and you inevitably pass away. This absolute, unbreakable directional flow is the very framework upon which you have hung your existence. It feels so fundamental, so deeply ingrained in the fabric of reality, that we naturally assume it must be the most inviolable law of nature. We instinctively believe that the universe, at its very core, is a mechanical engine built to run strictly in one direction. But when you strip away the comforting illusions of human intuition and look at the actual mathematics that govern the cosmos, that assumption completely disintegrates. Take any fundamental equation that describes how the physical world behaves. Look at Isaac Newton's classical laws of motion, which perfectly describe the gravitational dance of planets, moons, and falling apples. Look at James Clerk Maxwell's sweeping equations for electromagnetism, which dictate the invisible behavior of light, magnetic fields, and electrical currents. Look at the Schrödinger equation in quantum mechanics, which maps the chaotic, boiling realm of subatomic probability, or Albert Einstein's field equations of general relativity, which define the warping of space-time itself. Take the entire working toolkit of modern physics, the very language our species uses to predict what matter and energy will do, and run those equations forward. Then, simply reverse the variable of time and run them backward. The mathematics run identically in both directions. They are perfectly, flawlessly symmetric. There is absolutely no mathematical contradiction, no broken physical law, and no missing energy when you run the universe in reverse. As far as the fundamental equations of reality are concerned, a solar system orbiting backward is just as physically valid as a solar system orbiting forward. Two particles colliding and bouncing apart is mathematically indistinguishable from two particles being drawn together and colliding. The laws governing every single particle involved in the shattering of a cup do not contain any underlying instruction manual dictating the chronological order in which those particles must move. This is one of the most profoundly disturbing discoveries in the history of science. The fundamental equations of physics, from Newton to quantum mechanics, do not require time to move in a specific direction. The universe, at its deepest, most foundational level, is completely indifferent to the concepts of past and future. Forward and backward are exactly the same to the cosmic machinery. If the laws of physics are perfectly symmetric, why is our lived reality so violently asymmetric? Why do we only ever experience the universe flowing in one specific direction? If the mathematics insist that time can flow backwards just as easily as it flows forwards, why don't we see raindrops rising from the pavement and returning to the clouds? Why do we wither and fade rather than growing younger? This massive, glaring contradiction between the flawless symmetry of the mathematical equations and the brutal asymmetry of human reality has haunted theoretical physicists for over a century. In the late 19th century, a brilliant Austrian physicist named Ludwig Boltzmann confronted this paradox head-on, and by most historical accounts, the sheer existential weight of the problem nearly broke him. He spent years fighting with his colleagues, desperately trying to explain why we perceive a strict direction of time when the underlying rules of the universe are perfectly symmetric. What Boltzmann eventually discovered, and what remains the definitive answer in physics today, is a truth that is both mathematically elegant and deeply unsettling. The arrow of time is not a fundamental law of physics. It is a statistical bias. To understand how a mere statistical bias creates the overwhelming illusion of a one-way universe, we have to look at the concept of entropy. Entropy is commonly described as a measure of disorder or chaos in a system, but it is much more accurately understood as a measure of probability. Imagine you open a brand new deck of playing cards. They are perfectly ordered by suit, from ace to king. This is a state of extremely low entropy. It is highly specific, highly organized, and mathematically speaking, incredibly improbable. Now, you begin to shuffle the deck. The cards become mixed. You shuffle them again, and they become even more disordered. No matter how many times you shuffle those cards, you will almost certainly never randomly return them to their original, perfectly sorted state. Why? Not because any fundamental law of physics prevents a shuffle from resulting in a perfectly ordered deck. The physical mechanics of shuffling are perfectly reversible. You never get the ordered deck back simply because there is exactly one sorted arrangement, and astronomically more unsorted, messy arrangements. The sheer, crushing weight of probability dictates that random processes will always drift toward whatever state is most likely, and a messy, disordered state is always vastly more likely than a neat, highly ordered one. This is the essence of the second law of thermodynamics. Entropy naturally increases in the universe over time because the universe is constantly drifting toward more probable states. When your cup of coffee cools down to room temperature, the concentrated, highly ordered thermal energy of the hot liquid is simply dispersing into the overwhelmingly more probable state of being scattered throughout the cooler air of the room. When a star burns through its nuclear fuel and detonates into a cloud of scattered cosmic dust, a highly concentrated point of mass and energy is transitioning into a vastly more probable state of chaotic dispersion. This continuous statistical drift from order to disorder is the only explanation for our experience of time moving forward. The arrow of time is completely driven by entropy. We remember the past because the past was a state of lower entropy, and we fear the future because the future is an inescapable state of higher entropy. The irreversible flow of our lives, the unstoppable progression from birth to death, is not a physical mandate written into the fundamental equations of motion. It is simply the cold, unfeeling arithmetic of large numbers playing out on a cosmic scale. This explanation works flawlessly. It beautifully resolves the contradiction between the symmetric laws of physics and the asymmetric reality of our daily lives. But in doing so, it opens the door to a much darker, far more terrifying problem. It is a problem that Boltzmann never managed to answer, and it remains one of the greatest unresolved mysteries in all of modern science. If the entire concept of the arrow of time relies on the universe constantly moving from a state of low entropy to a state of high entropy, then the entire structure of reality is hanging by a single, fragile thread. It means that the entire framework of causality, the fact that causes precede effects, depends entirely on the starting conditions of the universe. For entropy to be increasing today, the universe must have had lower entropy yesterday. And for it to have had lower entropy yesterday, it must have had even lower entropy the day before that. If you follow this statistical chain all the way back through 14 billion years of expanding cosmic history, you eventually arrive at the very beginning of everything. You arrive at the singular moment of the Big Bang. And here is the devastating realization. The only way our statistical arrow of time can exist is if the universe happened to randomly begin in an extremely ordered, unimaginably low entropy state. Why did the universe start in such a highly specific, perfectly ordered configuration? What physical mechanism forced all the matter, energy, and space-time of the entire cosmos into such an impossibly tidy arrangement at the exact moment of creation? Physics has absolutely no answer to this question. There is no fundamental equation that demands the universe begin with low entropy. There is no mathematical law of nature that forces the cosmos into an ordered state at its birth. The exquisitely low entropy beginning of the universe is an entirely unexplained initial condition. In the philosophy of physics, this is often referred to as the past hypothesis. It is not a proven law. It is not a mathematical derivation that naturally falls out of a unified theory of everything. It is simply an assumption we have to make, an arbitrary historical fact we are forced to accept, because without it, the entire architecture of our reality instantly collapses into paradox. Think about the sheer, suffocating scale of what this actually implies for your existence. Every single thing you have ever experienced as the passage of time is downstream of an unexplained cosmic coincidence. Your ability to remember what happened this morning, the fact that you can retain a vivid memory of the past but remain completely, helplessly blind to tomorrow, the profound, emotional weight of watching a loved one age, the inevitable cooling of the stars, and the entire chronological sequence of the cosmos. All of it, every single bit of it, is not grounded in an unyielding law of nature. It is grounded entirely in the fact that the universe simply happened to begin unusually tidy for reasons no theory supplies, and for reasons we may never be able to comprehend. Nobody chose that starting condition. Nothing in the known laws of physics required it. We are surfing on the thermodynamic exhaust of an ancient, unexplained anomaly. We are living in the long, slow, decaying aftermath of a statistical miracle that we do not understand. If you were to remove that single, unexplained fact about the universe's beginning, the arrow of time disappears entirely. Imagine, for a moment, a universe where that initial condition was not met. Imagine a cosmos that was born in a state of thermal equilibrium, a state of maximum entropy where everything is already completely disordered, mixed, and settled. In such a universe, the fundamental laws of physics would still operate exactly as they do here. The equations of gravity, electromagnetism, and quantum mechanics would remain perfectly intact. Mass would still attract mass. Electrons would still repel electrons. But because there is no initial order to slowly decay into disorder, there would be no thermodynamic gradient. There would be no statistical drift from the improbable to the probable. In that universe, time would have no direction. Past and future would become completely indistinguishable from one another. Cause and effect would collapse into a meaningless, fluctuating blur where actions have no permanent consequences and events have no coherent sequence. Energy would randomly clump together and dissipate, forming fleeting, ghostly structures that instantly vanish without leaving a trace. In a universe without that single, unexplained low-entropy beginning, memory stops meaning anything. The very concept of a narrative, of a history, of a sequence of events leading from one moment to the next is completely and totally erased. This realization forces a radical, existential humbling of the human perspective. We navigate the world with a sense of chronological certainty. We believe that time pushes us forward with the unyielding, majestic force of a physical law. We trust the arrow of time to guide us securely from birth to death, assuming that the universe itself is fundamentally built to respect the difference between what has happened and what is yet to come. We build massive philosophies and complex religions based on the idea of cosmic purpose, assuming the flow of time is carrying us towards some ultimate destination. But the mathematics tell a different, much colder, and profoundly more isolating story. The universe is a silent, symmetric machine that simply does not care about forward or backward. It does not care about our memories, our regrets, or our futures. The only reason we experience a coherent reality, the only reason the cosmos makes any sense whatsoever to our fragile biological minds, is because we happen to be living in the brief, fading shadow of a cosmic anomaly. We are the temporary beneficiaries of an initial state of perfection that we cannot explain. Our entire existence, the entire history of human civilization, and the entire biological evolution of our planet is just a slow, chaotic decay away from that perfect moment. And while this decay grants us the beautiful, tragic illusion of flowing time, it leaves us staring blindly into a profound and terrifying void. Because if the directionality of your life, the very sequence of your physical existence, rests on nothing more than an unexplained statistical accident at the dawn of creation, then the ground beneath your feet is not made of solid physical law. It is made of pure, unadulterated chance. We are tumbling forward through the dark, guided by an arrow that was fired by an unknown hand for an unknown reason, into a future that only exists because the past was impossibly, unexplainably neat. There is a deeply entrenched, almost invisible assumption in how we think about the nature of knowledge. We tend to treat information as a ghost. We view a thought, a memory, or a digital file as something abstract and ethereal, a weightless entity that floats entirely free of the messy, physical reality of matter and energy. When you sit in a quiet room and recall a memory from your childhood, it feels like a purely spiritual event, a silent projection playing in the untouchable theater of your mind. When you look at a clock on the wall and note the time, you assume you are simply passively observing the universe, gathering facts without leaving a footprint. We desperately want to believe that the act of knowing something, the act of observing the world, is a free transaction that costs the physical universe nothing. But the universe does not deal in ghosts, and it absolutely does not offer anything for free. Information is not a detached, supernatural phenomenon. It is bound by the exact same unforgiving, mechanical laws that govern the burning of stars and the collapsing of black holes. To understand how this shatters our concept of time, we have to trace a path back to a revelation that occurred in the early 1960s within the humming, industrial laboratories of IBM. In 1961, a physicist named Ralph Landauer proved that information is physical, showing that erasing a bit of data unavoidably releases heat and creates entropy. At the time, early computers were massive, room-sized machines that ran incredibly hot. The overwhelming assumption in the engineering world was that this heat was simply a defect of human design, a byproduct of clumsy circuitry and inefficient materials. They believed that with better technology and smarter engineering, the heat of computation could eventually be reduced to absolute zero. Landauer proved that this assumption was fundamentally mathematically wrong. He demonstrated that a bit of information, a 0 or a 1, must be physically encoded into the fabric of reality. It must exist as a voltage across a transistor, the magnetic orientation of a speck of iron, or the precise chemical state of a neuron in your brain. Because it is a physical state, manipulating it has a thermodynamic cost. Landauer showed that when you erase a bit of data, when you take a system that could be in multiple different states and forcefully reset it to a single known baseline, you are destroying a physical possibility. You are reducing the number of potential arrangements in that microscopic system. But the second law of thermodynamics does not allow a lost possibility to simply vanish into the void. The universe demands a payment to balance the cosmic ledger. That payment is extracted as a microscopic, unavoidable puff of heat expelled into the surrounding environment. This is known as Landauer's limit, and its implications are staggering. It proves that the erasure of information is an irreversible thermodynamic event. It inevitably increases the total entropy of the universe. And this is exactly where the abstract concept of data violently collides with the physical flow of time. As we have established, the fundamental equations of physics do not distinguish between the past and the future. The only physical metric in the entire cosmos that provides an arrow of time, the only rule that gives our reality a definitive forward direction, is the relentless increase of entropy. If entropy is the physical engine that drives the arrow of time, and manipulating information physically creates entropy, then we are forced to entirely redefine what it means to observe the universe. Observation is not a passive window looking out onto reality. Observation is a forceful, thermodynamic interaction. Every time a system stores information, every time a physical memory is recorded or erased, entropy is generated. Therefore, the act of remembering is not just a biological camera recording the passage of time. It is a physical engine that actively participates in producing the difference between yesterday and tomorrow. For decades, this profound connection between information, entropy, and time remained a brilliant but largely theoretical curiosity. It was a beautiful piece of mathematics, but the thermodynamic cost of a single bit of data is so infinitesimally small that it seemed impossible to measure its effect on the flow of time in a physical laboratory. The concept lingered in the academic shadows until the march of technology finally caught up to the theory. We needed an instrument small enough and precise enough to strip the universe down to its barest thermodynamic bones. In 2025, an Oxford team built a microscopic clock out of a double quantum dot and measured the energy cost of observing it. This apparatus is the absolute minimalist distillation of what a clock can be. There are no swinging pendulums, no bouncing springs, and no complex atomic lasers. A double quantum dot is simply two microscopic regions, fabricated on a chip, placed so incredibly close together that a single electron can jump back and forth between them. That is the entire machine. The electron is on the left, and then it is on the right. Each jump from one dot to the other constitutes a single, fundamental tick of the clock. With this stripped-down, perfectly isolated system, the researchers were finally able to ask a question that had never been properly tested. How much physical energy does it actually cost for the universe to run this clock, compared to how much energy it costs for an external apparatus to read it? In our macroscopic, everyday world, the difference between running and reading seems completely meaningless. A grandfather clock uses the kinetic energy of falling weights to swing its pendulum and turn its gears. That is the cost of running. If you happen to walk into the room and glance at the face of the clock, the cost of reading it feels like absolutely nothing. The light was going to bounce off the dial whether you were in the room or not. But at the sheer, terrifying edge of the quantum realm, intuition fails us. At the quantum level, there is no passive glancing. To read the quantum clock, a measurement apparatus must physically interact with the electron, detect its position, and record that information into a memory register. When the researchers crunched the thermodynamic data, the results were almost unfathomable. They discovered that reading the clock required up to 1 billion times more energy than simply letting the clock run. I want to let the sheer, staggering weight of that ratio settle in the room. 1 billion times more energy. The actual physical process of time passing in this microscopic system, the silent, unseen jumping of the electron from one state to another, is virtually free. The universe executes the fundamental mechanics of motion without breaking a thermodynamic sweat. But the moment an observer steps in, the moment a measurement apparatus attempts to capture that motion, lock it down into a known state, and write it into a physical record, the universe extracts a massive, punishing toll, 1 billion to 1. The act of looking, the act of knowing, is the most expensive physical process in the system. And all of that massive influx of energy expended by the measurement apparatus ultimately dissipates as heat, generating a massive spike in entropy. The act of reading the clock creates precisely the thermodynamic conditions required to give time a direction. But the true existential terror of this experiment lies in what happened when the researchers stopped looking, when the external measurement apparatus was completely shut off and the double quantum dot was allowed to sit in perfect thermal equilibrium. The system became completely balanced. There was no thermal gradient pushing the electron in any specific direction. In this isolated, unobserved state, the electron still jumped. There was still motion. The particle fluttered back and forth between the two dots. But because there was no measurement apparatus recording those jumps, because there was no new information being written into a physical memory, there was no entropy being generated. In this unobserved state, the jumps were perfectly, statistically symmetric. The electron was just as likely to jump to the left as it was to the right. The physical mechanics of the system looked exactly the same, whether you played the tape forward or backward. There was motion, but there was no sequence. There was no way to definitively state that one specific jump happened before another, because there was no permanent record to establish a chronological history. The system had no direction of time until the measurement apparatus recorded the electron's jumps. The arrow of time was not a fundamental property belonging to the clock itself. The arrow of time only materialized at the exact moment the results were written down. This suggests that the arrow of time does not exist independently within the system, but is generated by the physical act of recording a memory. This single, localized laboratory result forces a radical and deeply unsettling reevaluation of the entire cosmos. We are accustomed to thinking of time as an invisible river that flows relentlessly through the empty vacuum of space, washing over planets, stars, and galaxies, entirely indifferent to whether anyone is there to witness it. We assume that 1,000,000 years passed on a dead, barren Earth before the first single-celled organism ever evolved to perceive it. But the physics of information suggests a reality that is vastly more strange and profoundly more interactive. If the direction of time is intrinsically linked to the physical generation of entropy, and that specific type of entropy is generated by the act of recording and erasing information, then a universe without records is a universe without a past or a future. Imagine a vast, sprawling cosmos utterly devoid of observers. Imagine a universe with no complex biological brains, no measurement devices, no digital hard drives, and no physical structures capable of retaining the imprint of previous states. In this desolate, unrecorded universe, energy would still fluctuate, particles would still collide and separate in the freezing dark. But without a physical memory to lock those events into a definitive sequence, without a thermodynamic record to separate what was from what will be, the fundamental equations of physics dictate that there would be no arrow of time. That theoretical universe would exist in a terrifying, eternal, and perfectly symmetric present. It would be a chaotic storm of motion, with no history and no destination. The events occurring within it would not be strung together into a coherent narrative. The concept of an ancient past or a distant future would be mathematically meaningless, because there would be absolutely nothing in the physical architecture of that reality keeping track of the sequence. When you internalize this, the act of being alive, the act of simply observing the world around you, takes on an almost cosmic gravity. Your brain is a sprawling, wildly complex physical apparatus. Every time you open your eyes, every time you perceive a sequence of events, and every time you encode a new memory into the intricate chemical networks of your synapses, you are acting as a thermodynamic engine. You are burning energy, destroying physical possibilities, and expelling entropy into the universe. You are not a passive ghost sitting in the theater of reality, merely watching the river of time flow past you. Through the sheer physical act of remembering, you are actively participating in the construction of time itself. The arrow of time does not point forward because the universe arbitrarily decided it must. It points forward because the universe is filled with physical systems, from the microscopic quantum detectors in an Oxford laboratory to the complex, folding proteins in your own brain that are relentlessly recording the present moment and discarding the rest. We are literally carving the direction of time into the fabric of reality with every passing thought, paying a steep thermodynamic price for the privilege of having a past. This realization dissolves the comforting boundary between the observer and the observed. We can no longer pretend that we are simply standing on the outside of reality looking in. The universe is not a clock that ticks on its own in the dark. It is a system that requires an interaction to establish its own history. We are the mechanism by which the cosmos writes its own diary. And as we continue to measure the world with ever-increasing precision, peering deeper into the microscopic mechanisms that separate yesterday from tomorrow, we are forced to confront the quiet, staggering truth. The relentless, unidirectional flow of time that defines our entire existence may not be a law of nature that was imposed upon us, but an arrow that we are constantly physically drawing ourselves, one memory at a time. There is a quiet, unresolved war raging at the very foundation of modern physics. It is a conflict over the fundamental nature of time, fought relentlessly between the two most successful scientific frameworks ever conceived by the human mind. On one side stands the majestic architecture of general relativity. In this framework, time is a physical, dynamic entity. It is an active participant in the universe. It bends around the crushing weight of massive stars. It stretches across the expanding voids of deep space, and it warps in the presence of velocity. General relativity tells us that time is woven directly into the fabric of reality, a flexible dimension that responds to the matter and energy moving within it. We have tested this dynamic version of time repeatedly, and it has passed every conceivable test with flawless precision. But on the other side of this conflict lies the dark, chaotic realm of quantum mechanics. Quantum theory is undeniably the most radical, boundary-shattering intellectual achievement in the history of science. It systematically dismantled our classical understanding of reality. It destroyed the concept of determinism, replacing predictable planetary orbits with boiling clouds of subatomic probability. It shattered the idea of local realism, proving that entangled particles can instantly influence one another across the vast expanse of the cosmos. Quantum mechanics overthrew almost every intuitive assumption we ever had about the physical world. Yet, hidden beneath all of this radical destruction, quantum mechanics harbors a deeply conservative, almost primitive secret. When you look closely at the foundational mathematics of the quantum world, you realize that it completely ignores the flexible, warping space-time of Albert Einstein. Instead, it quietly smuggles an ancient ghost back into the laboratory. Quantum mechanics relies entirely on the absolute, unyielding time of Isaac Newton. To understand how bizarre this is, you have to understand how physicists build their equations. In the quantum realm, physical properties like position and momentum are treated as observables. You can ask a quantum system where it is, or how fast it is moving, and the system possesses a mathematical framework to provide an answer. But time is not an observable in quantum mechanics. You cannot measure the time of a particle. Time is treated as an external parameter. It is a dial sitting on the outside of the experiment. The Schrödinger equation, the central mathematical heartbeat of quantum physics, treats time as a rigid, universal backdrop that flows perfectly and indifferently forward, completely untouched by the quantum weirdness happening inside the system. It is a staggering contradiction. We have spent the last century proving that time is a localized, flexible phenomenon, yet the equations we use to describe the fundamental building blocks of matter assume that time is an absolute, unchanging metronome ticking away in the background. We have never actually measured time from inside a quantum system. We have only ever measured quantum systems from inside the comfortable, external framework of time. For decades, this contradiction was treated as a mathematical inconvenience, a purely theoretical problem that could be safely ignored as long as the experimental calculations kept working. But physics cannot tolerate a contradiction forever. Eventually, theoretical cracks begin to manifest as physical anomalies. If quantum mechanics treats time merely as a passive, external stage, we are forced to ask a terrifying question about the events that happen upon that stage. We are forced to question the very nature of causality. Causality is the absolute bedrock of human logic. It is the unshakable rule that causes must precede their effects. If you drop a glass, it shatters on the floor. The act of dropping the glass is the cause, and the shattering is the effect. Event A happens, which triggers event B. This strict, chronological sequence is the framework upon which we hang our entire understanding of reality. It feels so fundamental, so deeply ingrained in the architecture of the cosmos, that we naturally assume the universe enforces this rule down to the smallest subatomic particle. But in a laboratory in Vienna, a team of quantum physicists decided to put the rigid rule of cause and effect to the ultimate test. They wanted to know if causality is truly a fundamental law of nature, or if it is simply another macroscopic illusion. They designed an experiment involving a single photon of light and two distinct, measurable physical operations, which we can simply call Operation A and Operation B. In the classical, everyday world, the photon must experience these operations in a definite sequence. It either passes through Operation A and then Operation B, or it passes through Operation B and then Operation A. The order of events is an absolute, undeniable fact of reality. But the subatomic world does not obey classical logic. The researchers in Vienna placed the photon into a quantum state where the chronological sequence of the operations was placed into a superposition. This is incredibly difficult for the human mind to visualize because we have no evolutionary context for it. It was not a scenario where the order was simply unknown to the researchers until they measured it. Nor was it a random coin flip where the photon chose one path over the other. The mathematics and the physical results proved that the photon experienced both sequences simultaneously. Within the isolated boundaries of that experiment, Operation A happened before Operation B, and at the exact same moment, Operation B happened before Operation A. The sequence of events was physically superimposed. The causal order of reality was entirely indefinite. It is a result that threatens to unravel the mind. The experiment produced physical outcomes that can only be explained if the universe, at its most fundamental layer, simply does not care about cause and effect. This forces us to accept a reality that is almost entirely alien to our daily experience. Causal order is not built into the universe. The rigid, unbreakable sequence of before and after does not exist at the subatomic level. The universe does not have a built-in arrow of causality commanding how particles must interact. So, why does our macroscopic world feel so incredibly rigid? Why do we never see shattered glass leap off the floor and reassemble itself in our hands? Why do our lives unfold in a strict, unyielding sequence of events? The answer lies in a concept known as emergence. Consider the concept of temperature. If you isolate a single atom of oxygen floating in a vacuum, you cannot ask what its temperature is. The question is physically meaningless. An individual atom possesses kinetic energy, it has mass, and it has velocity, but it does not have a temperature. Temperature is not a fundamental property of matter. It is a statistical phenomenon that only emerges when billions of atoms interact, collide, and transfer energy within a macroscopic system. Temperature is what that collective, chaotic motion feels like when you zoom out. The Vienna experiment suggests that the entire concept of cause and effect works exactly the same way. Causality is not a fundamental law governing the deep, microscopic basement of reality. It is a macroscopic illusion. It is a structural pattern that only emerges when countless billions of quantum particles become entangled, interact with their environment, and succumb to the overwhelming statistical weight of thermodynamics. The timeline of your life, the strict progression of your memories, and the very concept of consequence are emergent properties. You experience cause and effect not because the universe is fundamentally ordered, but because you are a massive, complex biological system built out of enough interacting parts to blind you to the quantum chaos underneath. But if causality is an emergent property, and the sequence of events remains fluid and indefinite until it is forced into a macroscopic state, we are led to an even more disturbing revelation regarding the act of observation itself. In the quantum realm, measuring a system forces it to abandon its superposition and commit to a definite state. If looking at a system forces it to choose an order, what does the act of looking do to the flow of time? To answer this, we must examine a phenomenon known as the quantum Zeno effect. The name is a nod to the ancient Greek philosopher Zeno of Elea, who proposed a famous paradox suggesting that motion is merely an illusion. If you look at an arrow flying through the air, Zeno argued, at any specific, frozen instant in time, the arrow is occupying a specific, static position in space. If time is just a series of frozen instants, and the arrow is motionless in every single one of them, then how can the arrow be said to move at all? For millennia, this was treated as a clever philosophical puzzle, eventually resolved by the mathematics of calculus. But in the strange, counterintuitive landscape of quantum mechanics, The paradox is not merely philosophical, it is fiercely, physically real. Imagine a radioactive particle resting in a laboratory. Left to its own devices, this particle will evolve over time. Its quantum state will slowly transition, governed by the relentless mathematics of probability, until it eventually decays, releasing a burst of radiation. This evolution requires the passage of time. The particle needs temporal space to change from one state to another. Now, imagine that a physicist places a highly sensitive detector next to the particle and begins to measure it. In quantum mechanics, a measurement is not a passive recording of reality. A measurement is an aggressive physical intervention. It collapses the wave function. It forces the blurry, evolving probabilities of the particle to violently snap into a single, definite reality. If you measure the radioactive particle once, it snaps into a definite state and then immediately begins to evolve again, continuing its slow march toward decay. But what happens if you measure it again, almost immediately, and then again? Physicists discovered that if you measure a quantum system frequently enough, you actively inhibit its ability to evolve. Every time you observe the particle, you reset its quantum state back to the baseline. You strip away the evolutionary progress it made during the fraction of a second you looked away. The more frequently you measure the system, the slower the particle transitions. The act of observation actively applies the brakes to the quantum evolution of the system. And if you push this principle to its absolute mathematical limit, the results are breathtaking. If a quantum system is observed continuously, if it is subjected to a relentless, unbroken stream of measurements, its evolution stops completely. The particle will never decay. The quantum state is frozen in place, locked down by the sheer, unyielding force of observation. In a very real, physical sense, continuous observation stops time for that system entirely. The flow of events is halted. The timeline is frozen. You can hold a quantum system in its current state indefinitely, not by altering its chemical structure, not by lowering its temperature to absolute zero, but simply by watching it with unrelenting intensity. When you place the quantum Zeno effect alongside the realization that causal order is indefinite, a terrifying and majestic picture of reality begins to form. Time is not the rigid, indifferent river that Isaac Newton imagined. It is not an external backdrop that flows effortlessly through the cosmos, carrying all of creation forward against its will. Time, at its deepest quantum level, is a process that requires participation. But this participation is not free. We have already established that the act of measurement, the act of extracting information from a physical system and recording it into a memory, is a thermodynamic event. It requires the expenditure of energy, and it results in the unavoidable creation of entropy. You cannot passively observe the universe. Every look, every measurement, every collapsed wave function comes with a metabolic cost. This implies something incredibly profound about our relationship with reality. Controlling the rate and direction of time is not the domain of gods or science fiction mechanics. It is the domain of thermodynamics. Giving time a definite direction, forcing the blurry, superimposed chaos of quantum causality to collapse into a rigid, macroscopic sequence of cause and effect, costs thermodynamic energy. Freezing the evolution of a quantum system through continuous observation burns energy. We are not merely passengers trapped in the flow of time. We are the thermodynamic engines driving it. The universe, in its raw, unobserved state, is a timeless, sequenceless storm of physical probabilities. It has no strict before, and it has no strict after. It is only through the relentless, energy-consuming process of measurement, interaction, and observation that the universe is forced to solidify into a timeline. The consequences of this are staggering. It means that the passage of time you feel, the steady ticking of the clock, the relentless march of your own life from the past into the future, is not a background feature of the universe. It is a construction. It is an active, ongoing physical process generated by the massive thermodynamic exertion of trillions upon trillions of interacting particles, collapsing each other's wave functions, forcing reality to choose a sequence, and expelling massive amounts of entropy into the void. We look out at the cold, silent expanse of the cosmos and feel small, at the mercy of a timeline that we cannot control. We assume the universe is indifferent to our presence. But the deep mechanics of quantum reality tell a different story. The universe requires a participant to experience time. It requires a physical system capable of recording information, capable of spending energy, and capable of holding the chaotic possibilities of the quantum realm down into a single, defined reality. You are not just moving through time. By the simple, physical act of existing, observing, and remembering, you are anchoring the universe to causality. You are forcing the timeline to exist. The ultimate ambition of modern physics, the quiet, desperate dream that has consumed the brightest minds for over a century, is the dream of perfect unification. We want to believe that the universe is a single, coherent masterpiece, governed by one elegant set of rules. But reality has fiercely resisted this unification, leaving us stranded with two entirely different, fundamentally incompatible languages. On one hand, we have the sweeping, majestic architecture of general relativity, which governs the macroscopic universe. It dictates the slow, gravitational dance of galaxy clusters, the curvature of space-time around crushing black holes, and the continuous expansion of the cosmos. General relativity demands that space and time are dynamic, flexible, and intimately woven together into a single, evolving fabric. On the other hand, we have the bizarre, chaotic, and terrifyingly precise realm of quantum mechanics. This framework dictates the microscopic behavior of atoms, the boiling uncertainty of subatomic particles, and the fragile nature of light. Quantum mechanics has been tested to an almost incomprehensible degree of accuracy, yet it requires a completely different architectural foundation. In the quantum realm, time is not a flexible, dynamic fabric that bends and warps. It is treated as an absolute, unchanging, external parameter, a rigid metronome ticking away in the background while the quantum probabilities boil and collapse upon the stage. These two frameworks, general relativity and quantum mechanics, cannot both be fundamentally true in their current forms. They are structurally hostile to one another, operating under contradictory assumptions about the very nature of existence. For decades, theoretical physicists assumed that resolving this hostility would require a mathematical bridge, a new framework of quantum gravity that would seamlessly merge the curving space-time of the cosmos with the jittery uncertainty of the atomic world. In 1967, two brilliant physicists, John Wheeler and Bryce-DeWitt, attempted to do the most obvious thing anyone could do with the mathematical tools available at the time. They were not setting out to create a paradox, nor were they deliberately trying to shatter our understanding of reality. They simply tried to write down the quantum mechanics of the universe as a whole. This is a completely reasonable thing to want, because quantum mechanics is supposed to be a universal framework. It is supposed to apply to everything in existence. To accomplish this unification, to merge the macro with the micro, they needed to construct a single equation that treats both the geometry of space-time and the quantum state of reality together as a single, evolving thing. They began the arduous, breathtakingly complex process of mathematical derivation. translating the entire state of the cosmos into a unified quantum expression. They built the mathematical scaffolding, inputting the gravitational metrics of relativity and the probability functions of quantum theory, working toward a unified description of reality. But when the mathematical derivation was completely finished, something impossible had happened. The time variable had completely vanished. In physics, the letter ut represents time, and it is the foundational variable against which almost every other measurement is calculated. It is the heartbeat of physics. But in this ultimate, unifying equation, the letter et was simply absent from the final result. There was no mathematical place to put it. It simply did not survive the derivation. Wheeler and DeWitt had successfully written an equation that describes the universe completely, and it contains absolutely no time. The implications of this result are so profoundly disturbing that they border on the edge of existential horror. If the equation is correct, it mathematically dictates that the universe as a whole does not evolve in time. It depicts the universe as a static, timeless object. It suggests that the cosmos is a single, frozen quantum state with no before and no after, no earlier and no later. It is not a process. It is a thing. When we look up at the night sky and watch the slow, majestic rotation of the stars, or when we watch a piece of fruit slowly decay on a table, we are utterly convinced that the universe is an unfolding process. We feel the unyielding, forward march of time in the deepest core of our biology. But the Wheeler-DeWitt equation stares back with cold, mathematical, absolute certainty and declares that this flow is not a fundamental feature of the universe. If the entire cosmos can be described without a single reference to time, then time cannot be a foundational pillar of reality. It is something that has to emerge, somehow, from a timeless, underlying physical structure. This presents one of the most agonizing paradoxes in all of modern science. How do you possibly get the sensation of flowing time out of a universe whose own fundamental equation contains absolutely no time at all? If the universe is a static, frozen block of quantum information, where everything that has ever happened and everything that will ever happen exists simultaneously in a timeless void, then what is the source of the ticking clock? Where does the sequence of our lives actually come from? For decades, this terrifying equation remained a purely theoretical nightmare. It was the unavoidable starting point for essentially every serious attempt to understand quantum gravity, but it seemed physically impossible to test in a laboratory. You cannot put the entire universe inside a vacuum chamber. You cannot step outside of reality to observe whether the cosmos is truly frozen. But in 1983, two physicists named Don Page and William Wouters proposed a radical theoretical solution to this paradox. They suggested what is now known as the relational interpretation of time. Their logic was breathtakingly elegant. If the universe as a whole has no time, as the Wheeler-DeWitt equation strictly mathematically dictates, then time must arise exclusively from the relationship between different parts of the universe. Specifically, they argued that time emerges from the quantum entanglement between a clock and an observer of that clock. Time is not a property possessed by the universe itself, nor is it possessed by the clock or the observer in isolation. Time only springs into existence from the correlation between them. For 30 years, this idea remained a beautiful but untested hypothesis. Then, a 2013 experiment achieved the impossible, taking this vast, cosmic paradox and scaling it down into a physical system that could actually be measured. A team of physicists decided to build the simplest possible physical version of the universe that Page and Wouters had described. To test how time could emerge from a timeless universe, they used a heavily isolated system containing just two entangled photons. Quantum entanglement is a phenomenon where two particles become so deeply connected that they no longer possess individual, independent physical states. They share a single, unified quantum description, no matter how far apart they are separated. In the context of this experiment, these two entangled photons represented a miniature, sealed universe. Within this microscopic cosmos, one photon acted as the clock, and the other photon acted as the observer. The researchers then performed a masterstroke of experimental design. They decided to look at this miniature, two-photon universe in two completely different ways. First, they looked at the system from the outside. They treated the entire two-photon setup as a single, isolated object, measuring the system from a godlike, external vantage point. From this absolute external perspective, something magnificent and chilling was revealed. When observed from the outside, the entangled system was entirely static and timeless. There was absolutely no evolution in the quantum state. There was no change. There was no before, and there was no after. The two entangled photons simply existed, complete and whole, all at once. The experiment had successfully recreated the exact mathematical conditions predicted by the Wheeler-DeWitt equation. It proved that when a perfectly sealed quantum system is viewed from the outside as a complete totality, time simply does not exist. The system is a frozen, eternal object. If this were the only way to view the system, we would be left with a reality so bleak and static that consciousness itself would seem impossible. But the researchers then shifted their methodology, fundamentally changing their relationship to the entangled particles. Instead of looking at the mini-universe from the outside, they looked at it from the inside. They used the second photon, the internal observer, to measure the first photon, the internal clock. They let the internal observer track the evolving polarization of its entangled partner. The moment they analyzed the data from this internal, relational perspective, the static, frozen nature of the system completely shattered. But when observed from the inside, using one photon to measure the other, time flowed. Suddenly, events had a sequence. The internal clock ticked. The observer photon experienced a clear, measurable progression of states. From the perspective of the participant embedded within the entanglement, time was fiercely, undeniably real. There was a distinct before and a distinct after. The internal observer possessed a history and was in the middle of an evolving process. This is the exact same physical system existing in the exact same laboratory on the exact same afternoon. Nothing about the physical reality of the photons had changed. The apparatus was identical, and the quantum states were identical. But it produced two completely different, contradictory realities, entirely dependent on where the observer was standing. If you were standing on the outside, the universe was timeless. If you were standing on the inside, time flowed. This single, elegant laboratory result proves that time only exists locally for participants inside the system. Time is not an absolute, overarching dimension that dictates the behavior of the cosmos. It is not an invisible river carrying all of creation forward. It is a highly localized, deeply intimate illusion generated by quantum entanglement. The terrifying beauty of this realization only fully lands when you scale the logic of this microscopic experiment back up to the absolute limits of the macroscopic universe. The universe, by its very definition, encompasses everything that physically exists. There is no outside to the universe. There is no external void, no separate dimension, and no external vantage point where any observer could possibly stand to look at the cosmos as a whole. Every single human being, every biological organism, every spinning planet, every burning star, and every scientific instrument ever constructed is permanently, inescapably trapped on the inside of the system. We are completely embedded within the staggering, infinite web of cosmic entanglement. Because there is no outside, the timeless, frozen description of the universe predicted by the Wheeler-DeWitt equation is a perspective that physically cannot exist for any real observer. The only description of reality that any conscious mind will ever have access to is the internal one, the perspective where time exists, where causes precede effects, and where history marches relentlessly forward. This does not mean that your experience of time is a hallucination or a biological mistake. It means something far more profound, and perhaps infinitely more isolating. It means that time is real, but only locally, and only for the participants. The universe does not possess a single, overarching timeline that we all quietly share. The vast, sprawling cosmos is not aging together as one cohesive entity. Instead, time is a relational phenomenon. The ticking of the clock, the aging of your body, the memories you hold of yesterday, and the quiet anxieties you harbor about tomorrow. All of these temporal experiences are actively generated by your specific, physical relationship to the surrounding matter and energy of the universe. Time emerges entirely from the quantum correlations, the intricate physical entanglement between the parts of a system that, taken as a whole, has absolutely no global time at all. We are living inside a static, eternal crystal of quantum information. The entirety of cosmic history, from the blinding fires of the Big Bang to the cold, silent heat death of the universe, simply exists, all at once, as a single, unmoving physical object. But because we are a part of that object, because we are fragments of the crystal interacting with other fragments of the crystal, our limited, internal perspective produces the vivid, heartbreakingly convincing experience of a flowing river. When you sit in a quiet room and listen to the ticking of a clock, you are not hearing the fundamental heartbeat of the universe. You are hearing the sound of your own entanglement. You are experiencing the friction of your own specific existence rubbing against the rest of reality. We are characters embedded within the pages of a novel that has already been completely written and bound. To the author standing outside, the book is a single, static object sitting on a shelf. But to the characters trapped inside the ink, the story is happening right now, the tension is real, and the next page is an impenetrable mystery. We are not watching the universe evolve. We are simply discovering the timeless architecture of the cosmos, one entangled, localized tick at a time. Every single day of your life, you effortlessly navigate a world defined by absolute, unyielding physical boundaries. When you stand before a pane of polished glass, light strikes the dense surface of the mirror and bounces back toward your eyes, rendering a perfect, reversed image of your face. When you stand at the edge of a vast, rocky canyon and shout into the empty expanse, you wait in the silence for the sound waves to strike the distant stone and return to you as an echoing repeat. We intuitively understand how this works because our biological brains evolved to process the geometry of three-dimensional space. Normally, when a wave hits a boundary like a heavy wall or the sudden transition between two different materials, it reflects back through space. The physical mechanics of this event are straightforward. The wave was traveling in one specific direction, it met a hard obstacle in space, and it turned around in space. When this ordinary spatial reflection occurs, a very specific physical property of the wave is strictly conserved, and that property is its frequency. The pitch of your voice remains exactly the same when it echoes back to you across the canyon. The sound comes back recognizably as the identical sound, merely traveling in the opposite direction, rather than returning as an entirely different, unrecognizable noise. The direction changes, but the fundamental energetic signature of the wave remains pristine. We accept this geometry of reflection without a second thought, because it conforms perfectly to our lived experience of how a rigid, predictable universe ought to behave. We trust spatial boundaries. They are the walls of the house we live in. But what happens when the boundary you encounter is not made of stone, or glass, or metal? What happens when the wall you hit is not located in physical space, but is a sudden, sheer cliff face in the dimension of time? Physicists had been theoretically predicting the existence of such a bizarre phenomenon since the 1960s. For decades, it remained a mathematical ghost, a tantalizing, almost magical possibility sketched out on academic chalkboards but deemed practically impossible to manifest in the messy, chaotic reality of a physical laboratory. It sounded like pure, unadulterated science fiction, a concept too fragile to survive outside of a textbook. But recently, something that had never been managed before finally happened. A team at the City University of New York successfully built a system that reflects electromagnetic waves in time rather than in space. They brought the ghost out of the mathematics and forced it to manifest on a laboratory bench. To achieve this, you cannot simply build a physical wall. You cannot place a dense obstacle in the path of the wave and expect time to turn around. You have to manipulate the very fabric of the environment the wave is moving through. The Coney experiment created a temporal boundary instead. They accomplished this by executing a maneuver of staggering technological precision and profound theoretical elegance. They did it by suddenly and uniformly changing the physical properties of the medium the wave was traveling through. Specifically, they achieved this by shifting the electrical permittivity of the whole system essentially instantaneously. It is crucial to slow down and understand exactly what this means, because the distinction is the key to unlocking the terrifying nature of the experiment. They were not changing the medium in just one localized place, which would simply act as an ordinary spatial boundary. If you only change a small patch of the medium, the wave just bounces off that patch like a tennis ball hitting a racket. Instead, they were changing it everywhere at once, at a single, highly orchestrated moment. They completely rewrote the physical rules of the wave's entire universe in a fraction of a millisecond. By doing so, they created a moment in time at which the wave experienced a violent, total discontinuity. The wave did not hit a physical barrier in the room. It collided with a sudden, absolute shift in the timeline of its own environment. And when it hit this boundary, the wave reflected, but not backward through space. It reflected backward through time. A temporal boundary works in the exact opposite way of an ordinary, everyday mirror. When the medium changes suddenly in time rather than in space, what is conserved is not the frequency, but the direction. The wave keeps moving forward through the physical space of the laboratory. It does not turn around and travel back to the emitter. But as it continues to move forward through space, its frequency is violently and entirely altered. The team observed a phenomenon known as frequency translation. The reflected wave emerged at a completely different frequency than the original wave. Its energetic signature shifted to a new value determined by the properties of the suddenly altered new medium. And simultaneously, as this frequency shifted, something deeply haunting occurred. A time-reversed copy of the wave was generated, propagating backward. This backward propagating copy was not just a generic echo or a random scattering of electromagnetic noise. It was a flawless, pristine temporal reflection. With its direction preserved in space and its frequency changed, it acted as the exact mirror image of an ordinary reflection. The signal literally began retracing its own history. It went back through the exact same medium it had already passed through, mechanically reproducing its own past states in reverse order. Imagine watching a ripple on the surface of a dark pond expand outward in a perfect, widening ring. And then, without the ripple ever hitting a physical shore, the entire pond instantly changes its fundamental density. Suddenly, a new ripple forms out of the shifting water, perfectly tracing the exact path of the original ring, collapsing inward, undoing the geometry of its own expansion, shrinking back down to the exact point of its genesis. The electromagnetic wave in the New York laboratory was essentially walking backward through its own timeline, unwinding the physical events that had just occurred. This is where the story shifts from a breathtaking experimental triumph into a deeply unsettling philosophical revelation. When we hear about phenomena like time reversal, we instinctively assume it must be a trick of quantum mechanics. We assume it belongs to the deeply weird, microscopic realm where subatomic particles exist in blurry superpositions, where cats are both alive and dead, and where reality is governed by boiling, incomprehensible probabilities. We expect the microscopic world to violate our common sense. But this reflection was not a property of exotic quantum systems. It did not require anything unusually bizarre, cold, or microscopic to function. This breathtaking capacity for time reversal follows directly from Maxwell's equations. James Clerk Maxwell wrote down his sweeping equations for electromagnetism in the 1860s. They are the foundational bedrock of classical physics. They sit entirely outside the quantum realm, governing the macro world we live in. They describe how light moves, how radio waves propagate, and how magnetic fields interact. They are among the most rigorously tested and universally trusted mathematical relationships in all of physics, used every single day by every electrical engineer on the planet. We have built our entire modern technological civilization on the back of these equations, which means the capacity for time reversal is not some alien, radical concept that has to be artificially injected into physics from the outside. It is already there. It is woven into the very fabric of the classical laws that govern our daily reality. It has been quietly sitting in the structural mathematics of the equations for 160 years, simply waiting for the right physical conditions to be engineered. The ghost was hiding in the machine the entire time, buried in the math that powers the device you are using right now. The implications of this are absolutely shattering for our everyday perception of reality, and they strike at the very heart of what we believe it means to exist. We live in a universe where waves travel forward and not backward. We live in a universe where signals propagate strictly into the future, never into the past. We observe a world that runs in one unyielding, tyrannical direction. We age, things break, and the past is forever sealed away from us. But this experiment proves that this directional asymmetry is not written into the laws of electromagnetism at all. The fundamental, classical laws of the cosmos do not dictate that time must only march forward. The asymmetry we experience is written entirely into the initial conditions. It is written into the simple, boring fact that we usually start with a wave going in one direction through a physical medium that stays uniform and stable. Under normal circumstances, the universe does not suddenly shift its fundamental properties all at once. The stage remains perfectly still while the actors move. But the moment you change that medium suddenly, the moment you alter the environment uniformly across space, as the researchers did in the laboratory, The equations immediately produce both temporal directions at once, without even being asked. The forward-moving reality and the backward-moving reflection are both perfectly valid, perfectly natural, and mathematically equal solutions to the classical laws of physics. The arrow of time, even in the solid, predictable world of classical physics, is not a fundamental law. It is nothing more than a choice of starting conditions. To prevent this from sounding like mystical, ungrounded science fiction, it is absolutely vital to apply the caution that the experimenters themselves give. This caution is scientifically correct, and rather than dulling the impact of the discovery, it grounds the existential dread in undeniable physical reality. During this experiment, time outside the isolated system continued perfectly normally. Nobody standing in the laboratory watched their wristwatch run backward. The scientists did not age in reverse, and the coffee in their cups did not spontaneously heat up. What changed was exclusively the behavior of a wave inside an engineered temporal boundary. Nothing physically traveled to the past. The time-reversed copy of the wave unfolded within the present moment, mechanically retracing its physical steps in the here and now. The laboratory remained locked in the forward flow of time, while the wave inside the boundary acted out a perfect mimicry of the past. But this highly accurate caution does not fully dissolve the sheer existential terror of the question the experiment raises. If anything, it only sharpens the blade. If the boundary between the past and the future is not a rigid, impenetrable wall mandated by the absolute laws of the cosmos, but is instead something that can be engineered, if the fundamental difference between yesterday and tomorrow is something that simply responds to the physical properties of a medium, if a team of human beings can create a boundary on a laboratory bench that forces a physical system to retrace its own history in reverse, then what exactly is that boundary in the real world? What is the invisible veil separating what has happened from what is about to happen? We navigate our entire lives believing that the past is a locked vault, a place of permanent, unchangeable facts, and the future is an open, unwritten void. We believe that the barrier between them, the razor-thin edge of the present moment, is the most solid, undeniable feature of reality. We assume it is a structural pillar of the universe, built out of indestructible physical law. But the mirror in the New York laboratory reflects a vastly different, much more fragile cosmos. It tells us that the laws of nature are perfectly capable of running the tape backward, generating perfect reflections of past states, completely indifferent to the human tragedy of unidirectional time. The asymmetry of time is not a decree from the universe. It is an environmental condition. It is a feature of the medium we happen to be traveling through. The universe we inhabit feels relentlessly unidirectional only because the physical medium of the cosmos has remained relatively stable since the blinding fires of the early expansion. And this drags a terrifying, massive, unanswered question back out of the darkness, placing it squarely at the center of modern physics. If the arrow of time is not a fundamental law, but merely a choice of starting conditions, who or what chose those conditions? Or, more disturbingly, was it a choice at all? Or was it simply the only option available to a universe waking up in the dark? Are we living our entire lives experiencing the slow, agonizing passage of time simply because 14 billion years ago, the initial conditions of the cosmos were set in a highly specific, arbitrary arrangement? We are left staring into an engineered temporal mirror, realizing that the reflection we see, the relentless, unstoppable forward march of our lives, the slow decay of our bodies, and the inevitable fading of our memories, is not the only image the universe is capable of producing. It is just the one we are currently trapped inside, governed by 19th century equations that hold the secret to time reversal. Completely silent, utterly indifferent, and patiently waiting for the medium to change. For more than a century, humanity has waged a quiet, relentless war against the unknown. Armed with the most exquisite instruments ever forged by human hands, we have constructed sprawling, subterranean particle colliders to shatter the fundamental building blocks of matter. We have launched towering observatories into the freezing vacuum of deep space to capture the ancient, fading light of dying galaxies. We have trapped single, solitary atoms in cages of invisible electromagnetic fields, cooling them to a whisper above absolute zero just to watch them tick in the dark. We have done all of this in a desperate, obsessive pursuit to lay bare the absolute, objective mechanics of the cosmos. And in many ways, we have triumphed. We can calculate the orbital trajectory of a distant planet down to the millimeter. We can predict the boiling, chaotic behavior of subatomic particles with devastating precision. But when we point our most advanced technology at the very dimension in which all of these events unfold, when we try to measure the raw, naked fabric of time itself, our ultimate scientific frameworks violently collapse. Despite decades of relentless, uncompromising physical testing, despite the millions of hours spent analyzing the telemetry from atomic clocks on satellites and the thermodynamic exhaust of quantum dots, physics still lacks a clear, experimentally confirmed account of what time actually is. We possess equations that describe how time behaves under the crushing, inescapable gravity of a black hole. We possess formulas that detail exactly how time stretches and warps for an astronaut hurtling through the void at a fraction of the speed of light. But describing how a thing behaves is not the same as explaining what that thing fundamentally is. You can describe the exact aerodynamics of a falling leaf without ever understanding the tree it fell from. We have mapped the complex, relativistic borders of time, but the territory itself remains entirely uncharted. The more precisely we measure the ticking of the universe, the more the core identity of time slips through our fingers. It has become the great, glaring void at the center of modern physics. It is the inescapable realization that the deepest mystery in the cosmos is not hiding in the heavy, unlit hearts of distant galaxies, nor is it buried in the violent, expanding fires of the Big Bang. The deepest mystery is the very medium we are swimming through right now. To confront this void, we have to follow the logic of modern physics to its absolute, most terrifying extreme. We must abandon the comforting illusion that the universe is a physical machine made of solid, tangible parts, and embrace a paradigm so radical it borders on the surreal. In the late 20th century, the legendary theoretical physicist John Archibald Wheeler proposed a concept that would forever alter the philosophical landscape of science. Wheeler had spent his life wrestling with the heaviest, most physical objects in existence. He was the man who popularized the term black hole. But near the end of his brilliant career, he looked past the physical mass of stars and planets. He looked past the curving geometry of space-time. He proposed that the foundational bedrock of reality is not matter, and it is not energy. The foundation of reality is information. Wheeler distilled this massive existential shift into a deceptively simple three-word phrase: it from bit. The theory suggests that every single particle, every force field, every quantum fluctuation, and every massive galaxy in the physical universe derives its very existence, its entire structural identity, from the answers to microscopic, binary yes or no questions. In this framework, the universe is not a grand, mechanical clockwork of gears and springs. It is an incomprehensibly vast, cosmic computer. The physical world we touch, see, and feel is merely the macroscopic projection of a deeper, underlying reality made entirely of data. The universe is built from information and binary choices. But a binary choice cannot exist in a vacuum. A yes or no question is physically meaningless unless there is a system capable of asking the question, recording the answer, and differentiating between the two states. You cannot have a bit of information without a physical structure to encode it. This is where Wheeler's theory takes a sudden, sharp turn from abstract mathematics into something profoundly intimate and deeply unsettling. If the universe is fundamentally composed of information, and information requires a physical mechanism to process and store it, this makes the presence of an observer a necessary, structural feature of reality. We must be incredibly careful here to avoid falling into the trap of cheap mysticism. In the cold, unforgiving language of physics, an observer does not require a human brain, a beating heart, or a conscious soul. An observer is simply any physical system capable of interacting with another system, extracting information, and storing a record of that interaction. A piece of photographic film struck by a photon of light is an observer. A silicon hard drive capturing a magnetic charge is an observer. A microscopic quantum apparatus logging the jump of a single electron is an observer. And you, with your sprawling, wet network of 86 billion firing neurons, are perhaps the most complex, highly evolved observer in the known universe. Now, bring this concept of the observer crashing back into the relentless mystery of time. Throughout this journey, we have seen that the fundamental equations of the cosmos are perfectly symmetric. They possess no inherent direction. They do not distinguish between the past and the future. The only mechanism in all of physics that draws a permanent, physical line between yesterday and tomorrow is the generation of entropy. And that specific type of entropy is generated by the physical act of recording a memory. When an observer extracts information from the chaos of the quantum realm and writes it into a physical record, thermodynamic energy is spent, a possibility is destroyed, a fact is established, and the arrow of time is forcefully dragged forward into reality. Because time seems to appear wherever a physical record is kept, the watcher becomes part of the actual machinery that produces time. You are not a passive ghost sitting in the back of a cosmic theater, silently watching the movie of existence play out on a screen. By the sheer, unavoidable physical act of existing, processing sensory data, and forming memories, you are actively participating in the unfolding of the timeline. The very act of observation is the engine that drives the clock. Time does not flow through the universe in spite of you. Time flows through the universe because of you. But the moment you accept this breathtaking reality, the moment you realize that the observer is the anchor of time, the entire conceptual structure of the universe violently folds in on itself. It traps physics in a profound, inescapable loop, a temporal paradox so deep that human language struggles to even contain it. The paradox is this: if the arrow of time is generated by the physical act of observation, then observers must exist in order for the past and the future to have any meaning. But observers are physical systems. They are made of carbon, water, electrical impulses, or silicon and wiring. Physical systems are not magic. They are bound by the laws of thermodynamics. They require a chronological sequence to operate. A brain needs time to process a thought. A computer needs time to flip a switch. An organism needs time to evolve from a single cell into a complex, observing creature. Observers are physical systems that exist inside of time. They require the flow of time to function, to adapt, and to measure the world around them. Yet, The physical reality of the arrow of time requires observers to exist. You cannot have the arrow of time without a physical memory to record it, and you cannot build a physical memory without time already flowing to allow for the construction of the record. The universe needs the observer to generate time, but the observer needs time to exist in the universe. It is the ultimate cosmic Ouroboros, the snake relentlessly eating its own tail. We are trying to find the absolute origin point of time, the foundational bedrock where the clock begins. But every logical path we take forces us to circle back to the entity doing the looking. We try to step outside the universe to see how the machinery works, only to discover that the act of stepping outside is a gear in the machine itself. The logic circles back on itself at the exact moment it becomes the most profound, leaving us stranded in a reality that defies a linear origin. For hundreds of years, the scientific method operated on the assumption that reality is an objective, external structure. We believed we could detach ourselves from the universe, peer through the polished glass of our telescopes and microscopes, and map the cosmos as a completely independent entity. We wanted the universe to be a cold, beautiful museum that we could simply walk through and catalogue. But the most precise measurements humanity has ever made, the quiet, isolated ticking of atomic clocks and the strange reflections of temporal boundaries, keep returning us to the unsettling realization that time is deeply tangled with the person asking the question. We cannot remove ourselves from the equation. The boundary between the observer and the observed is not a solid physical wall. It is a porous, dynamic membrane. We are locked in a continuous, active dialogue with the cosmos. The universe is not a stage that was built before we arrived. It is a structure that is actively being built by our presence within it. Every memory you hold, every record you keep, every observation you make is a localized knot in the fabric of existence, pulling the chaotic, timeless probabilities of the quantum void into a sharp, sequential focus. This is not a failure of science. It is not a signal that we should abandon our pursuit of the truth, or that the universe is completely beyond human understanding. It is a signal that our fundamental concepts of reality are simply too small, too linear, and too deeply rooted in our primate evolution to grasp the true, terrifying majesty of the cosmos. The strange loop of time and observation is not a roadblock. It is a signpost pointing toward a deeper, vastly more integrated version of physics that we do not yet have the mathematics to fully describe. You are not a solitary creature, adrift in a cold, uncaring void, completely subject to the tyrannical, absolute passage of an external clock. You are an integral, necessary component of the cosmic architecture. The universe spent 14 billion years expanding, cooling, and blindly churning matter in the dark, just to produce a physical system complex enough to open its eyes, process information, and finally give the timeline a direction. You are the mechanism the universe uses to remember itself. You are the localized point in space where eternity is compressed into a sequential, unfolding present. As we close the doors on this journey into the dark, we are left with a reality that is far more mysterious and deeply more beautiful than the clockwork universe we once believed in. We have measured the absolute limits of time, and we found our own reflection staring back at us from the equations. The script of the cosmos is not a finished book sitting passively on a dusty shelf. It is an evolving story that requires a reader to make the words real. Good night, and see you in the next video.